Welcome everybody to the third unit of the fifth week in the Parallel Programming Concepts course. We discussed until here that in a shared nothing environment you have a particular kind of interconnection technology, particular kind of setup, and you need to consider task granularity in order to run a shared nothing application, shared nothing parallel application on your particular execution environment. The next interesting question now is, what are appropriate programming models in order to target such environments? So in week 3 we saw a lot of different ideas for programming in the shared memory world, such as OpenMP, Intel TBB, Silk and other ideas. In week 4 we saw how accelerators can be programmed with OpenCL. And here now the question is again, if we have this kind of execution environment with a shared nothing system, how do we target it? What are the available tools and programming paradigms? And in the kind of system that we want to cover in this course, clusters and supercomputers, there is a special kind of programming model that is established meanwhile, so it's something like the de facto standard, and this is message passing. Message passing as a programming paradigm is the idea of having applications that contain send, receive calls and other kind of message exchange primitives that allow the application to exchange messages. And you formulate such an application as a whole, as a piece of code, and then you use your cluster environment to run this on the machines. So an interesting infrastructure question in shared nothing environments is, how do you deal with all these different nodes sitting in your cluster? Do you really want to log into each and every single node and start a particular application instance so that all the different instances then can communicate with each other? This is not feasible. So the typical way of dealing with that is to have a cluster management software, cluster management system. There are different versions from different vendors, such as Grid Engine, Load Leveler, PBS, and others. So the underlying concept is always the same. You have a couple of machines being treated as a cluster, and you do not allow your users to log into them directly. Instead, you specify a particular submission host, and on the submission host, the users can compile their applications and then send it to the cluster management software. This is called a job, and this application job is then distributed on all the available execution hosts by the cluster management software. So the executable is either copied there or it's taken from a shared file system, and then on all these execution hosts, the application is started up. You get a particular application instance, and all these instances together then form the running parallel application. Inside this running parallel application, the different tasks, the instances, exchange their messages in order to synchronize their work, and at the end you get an overall result that is, for example, again written to a shared file system between the different nodes in the cluster installation. So this is a typical pattern, not only in local clusters and smaller clusters, but even in supercomputing environments, it more or less works like this. The overall idea in terms of the programming model is called single program multiple data. So since we have the situation that you do your code development and then you submit your code to the cluster management framework, you have to write your application in a way that a single piece of code can be instantiated multiple times on multiple machines and is still able to produce a particular result as a parallel application. And this works by the single program multiple data paradigm. So you take the same piece of code, you instantiate it multiple times. This is done by the cluster framework. And each of these instances is then covering a separate part of the input data. This is something you may already know from week 4 in OpenCL, where we have a similar idea. We have a large piece of data, and in OpenCL we have different instances of the same kernel that now operate on the data. The same situation happens here with single program multiple data in a shared nothing environment. You take your large piece of code, your large piece of input data, and then you run several instances of this program on the different shared nothing nodes and allow them to communicate with each other by messages. The programming model or the programming languages and libraries that support such a system were widely different in the early 80s and also in the 90s. And the problem there was that people use this and that messaging library or a facility in the language in order to program their shared nothing parallel application. This turned out to be very painful when you want, for example, to port a piece of code from one execution environment to the other, because the message passing libraries were specifically designed for the particular networking environment. So you have the situation that communication is the major pain point here. Therefore, your message passing library must be truly optimized for your interconnection technology. And this led to the fact in earlier times that you had a lot of different libraries for message passing inside your application. Since this was such a pain point, companies and universities started to do a collaborative effort in order to define a common programming interface and API for message passing in applications, and this is MPI, the message passing interface. So MPI is the definition of syntax and semantics for a messaging API. It allows you to write portable code that can be taken from one installation to the other, recompiled, and then run without modification. It is not targeting interoperability, for example, like HTTP, where you want to have multiple applications from different authors to communicate with each other. The idea that you want to achieve here is only portability, so I take my MPI source code and I can reuse it on another execution platform. The MPI approach is to have a fixed number of process instances, and they are defined on startup. So when you run your MPI application, you have to tell the system how many parallel instances you want to have. And then the cluster execution environment will take care of firing up all your different instances so that you can then use this level of parallelism in order to get some speed up in your application. MPI supports point-to-point communication between single nodes, but also collective communications, where a group of processes is doing all together a communication step. MPI is standardized by a consortium, as I said, the MPI Forum, and the latest version of the standard is from 2012, so this is still actively developed. Let's look into the details of how MPI works in practice. In MPI, each application instance, which is also called an MPI process, has a rank. The rank is a unique number inside a group of processes, and this group is called a communicator. Communicators are defined by default when you start up your application. There you have something that is called the world communicator. You can also define your own subgroups, but typically MPI applications rely on the world communicator in order to have all the different instances of the same application at reach. Inside the communicator, each and every process has a dedicated rank, so you can target a particular instance with your messaging by just using its rank number, and the underlying library will then know where this instance is living and how to route the message to this particular instance in the system. If you want to do point-to-point communication, the most basic primitives in the MPI API are MPI send and MPI receive. The examples here and in the other slides are all in C language. There are also language bindings to C++ and Fortran. MPI send and receive look very similar. They both follow a pattern where you hand over a buffer to the underlying message passing library. You also define the data type you want to transfer, and you define a particular rank. In the send API call, you define the destination rank. So what is the target number of the process instance I want to send the message to? And in the receive call, you tell the MPI library from which kind of instance you want to get a particular piece of information. Another parameter here is tag, which is an arbitrary message tag that allows you to further distinguish different communication attempts. So the source and destination of a send-receive couple are identified by tag, rank, and the particular communicator used. In the default send-receive semantics, the idea is that you always need to have a matching receive for a particular send. So tag, rank, and communicator of send and receive must match so that a real message transfer happens. If you don't have such a match, then the sender or receiver application will block in the particular call until the sending and receiving happens. This is actually a good thing because this makes sure that you have a synchronization point. So exchanging messages is truly an implicit barrier. It's an implicit synchronization because at least in the default versions of these two calls, Both applications will wait until the message exchange happens. So when the applications continue, they both know that they either sent the message or got the message. Here's a C code example for the use of MPI send and receive. The most relevant point is that you have a single piece of code, this piece of code, running in multiple instances. So a basic programming pattern in MPI is to have different behavior of your application depending on the local rank. So the rank was the unique number you get per instance, so therefore this number will differ in the different instances. And you see in the code that we do an if statement for the rank number, and depending on the fact whether we are rank 0 or not, we will behave differently. This example shows you a ring communication, so the idea is that one node is sending messages to the next higher rank, and it gets messages from the next lower rank. If you look through the code, you will see that you have to deal with the idea of having a rank 0, which then takes the values from the largest rank in the system. But overall, the basic pattern here that is most important is that you have different behavior with respect to the rank count. So you do not write separate programs for all the different ranks, but you write one piece of code that is prepared to be run in multiple instances. An interesting aspect in shared nothing systems is the question whether or not we get concurrency issues. We spent some time in week 2 to identify crucial concurrency problems we may have when we talk about parallelization, for example, race conditions or deadlocks. And the interesting question is now, can that happen in shared nothing too? So is it possible to have a deadlock in a messaging application, in a parallel MPI application, for example? And here you can see an example where this can actually happen. So we have, again, a different behavior depending on the rank. And on rank 0, we have the situation that we have 2 send calls with, you see the data type and the destination rank and the tag. So we have different tags here. And the rank 0 is first sending a message with tag number 1 and then with tag number 2. And the other rank, rank number 1, is first receiving a message with tag 2 and then receiving a message with tag 1. And since both of them now have the blocking condition, so send is waiting for a matching receive, and receive is waiting for a matching send, they will both deadlock. They will both wait for a particular condition, so the overall application will deadlock here with this piece of code, which shows us that the ordinary concurrency problems we saw in week number 2 can also happen in the shared nothing world. There's no difference. So whatever we have as a concurrency issue is valid both in shared memory programming for parallel applications and in shared nothing programming. So you have to consider this all the time, and we will see in later units what are possible ways to at least try to sneak around this problem a little bit. Going back to MPI, one point, as I said, is the point-to-point communication with send and receive and different variations of them with respect to buffering behavior. The more interesting part in MPI are the collective communication operations. So MPI supports a model where all the instances of our application do a collective communication attempt, either with one sender and multiple receivers, or multiple senders and one receiver, or even with a broadcasting situation where multiple senders send data to different receivers at a time, or to all. Collective communication is very important, especially when it comes to simulations or when you look into supercomputer applications. And it's also something that is very heavy in terms of communication overhead, because this is way more messages being exchanged than with a single point-to-point communication. So the interesting question is this something you want to have? And the answer is, if you use collective communication primitives in MPI, then the MPI library and the underlying interconnection topology has a chance to optimize this. So whether you want to do a broadcast or a scatter operation, the good point about using collective operations being defined in MPI is that you have the chance of getting all the optimizations from the interconnect hardware vendor and the MPI library offer that may be possible. So instead of doing such collective communications by yourself, for example, by looping with a point-to-point communication, it is more effective to use what you get in the MPI library, because then you get all the advantages from the particular implementation that is optimized for the execution environment. So let's go through a couple of collective operations that are defined in MPI. The first example is a barrier. We know the barrier concept already. We saw that with OpenMP, for example. And also in MPI, the semantics are the same. You have an MPI barrier statement inside of your code. The code is instantiated multiple times, runs on different nodes, and all these nodes now may have a different execution speed. Either you have heterogeneous nodes with different CPUs, or you have some blocking on one node that is not happening on the other node. And this leads to the fact that your progress of the different tasks is not lockstep, so you're not having equal process on all of the different hosts. And when you now have a situation in your application where you need to synchronize all the different activities, then you can establish a barrier, so you simply use the MPI barrier statement, and the library implementation will then make sure that in an efficient way, all the different instances are synchronized with each other in their execution speed. The next MPI primitive for collective communication is broadcast. So the MPI bcast call allows you to specify a buffer to be sent, or that should be used as the receive buffer, and a particular root rank. So the idea here again is that we have some piece of data on a chosen rank. You hand this rank to the API as a parameter, so it's your choice whether you want to do this from number 0 or something else. Since the mapping of ranks to nodes is not fixed, this is more a logical design issue and not a physical one that depends on the execution environment. So you define some arbitrary root rank, and the broadcast call is then executed on all the different instances. So you have your bcast call on all the different nodes, and the rank that has the particular root rank will then send the data from buffer to all the other ranks. So one of the instances is behaving differently because its own rank number now matches to the parameter that is given in the MPI bcast call. So the root rank is sending the content of buffer to all the other nodes, and the other nodes then have the data in their buffer variable after the call returns. So this allows you to broadcast data from one node to all other nodes in the system, including yourself. So all these collective operations also using the sender in addition as a receiver. The next collective operation that is available in MPI is scatter. Scatter allows you to send a larger data array to multiple target nodes by splitting up the data. So you take your array and you scatter your values to a couple of ranks, to a couple of processes. When you think, for example, about a farmer-worker scenario where you put out work to different nodes in order to have it computed in a parallel fashion, then this is a very efficient way, a single line way of distributing your work items. So you hand over a send buffer and a receive buffer. The send buffer is used on the defined root rank in order to read the data, to scatter it, and to send it to the receiving nodes. If you want to have equal parts, the standard scatter call is feasible, but there are also variations in the API to define different block sizes for different target ranks in your scatter call. The opposite API call to scatter is the gather call. In gather, you are able to fetch different data items from different other instances to one particular instance. This instance is again the root rank, so you define it in the call. And each of the processes, including the root process, so this looks like a pattern here, sends the data in its send buffer to the root rank node. The root rank node then has all the data in its receive buffer, typically ordered by the rank number, and then it can do a further processing on this receiving buffer. So with scatter, you fan out data items, you fan out work, and with gather, you collect the results again at one point in order to do a final calculation or final determination of an application result. A specialized version of gathering data is reduction. This is something that is not only available in MPI, but also, for example, in OpenMP as a primitive. The idea of reduction is to have a gather operation combined with some kind of aggregation. So you gather different results, different data items from other ranks, And while you're doing this, you also perform an aggregation operation on this data. For example, summing them up, multiplying them, or determining a minimum value. This aggregation operation must be one that has no dependence on ordering. And if this is given, then the MPI implementation can start to do optimizations for this kind of reduction. So while the data is gathered, the library now has the chance to do, for example, on-the-fly aggregation of data that is still in transport, and then giving you already the final aggregate on the target node. So reduction is a clever and nice way to express your intent to the library, to say, I want to have a reduction operation here in this part of the code, but to rely again on the implementation to do the heavy work, to do the real optimization. And this is a very smart way to deal with all kinds of aggregate functions, because MPI can here overlap computation and communication, so you don't have to do this in your application by yourself. Here's a very simple example, again, in C programming language. Main is our entry point to the program, so we see that this code is again running on all the different nodes. So we have different ranks, but the same code. And the first is an MPI scatter call that takes the input array, which is called data here, sliced, and then this one is sliced, and the parts are sent to all the other ranks. So everybody now gets a particular piece of data in its receive buffer. The scatter call leads to a receive operation on the non-zero ranks. And after we have the scatter call finished, everybody has a single piece of data. The next thing we do then is a reduction call. So we take back all the values from the different nodes, but we define an MPI prod argument here, which stands for product. So we tell MPI, please get all the data items back again from all the different racks and multiply all of them and come out with the result of this, and then we can print the result. So we're using here the MPI capability of fanning out the work and multiplying this. This is a toy example because the communication overhead is way too heavy. You would be much faster with a serial version of this problem. But if you now think about having some heavy operation between the scatter call and the reduce call, you see that this is a real advantage in order to parallelize your work in a shared nothing environment. What else do we have? MPI is a very complex standard. It has hundreds of functions defined, but the principal ideas we saw here are the foundation of all these things. MPI has variations for send and receive for the point-to-point communication, where you can influence the buffering behavior of the networking stack in a very fine-grained way, so you get very efficient ways of optimizing your performance. You have things like all-gather, all-to-all, so more specialized versions of collective communication. MPI supports, meanwhile, virtual topologies, so you can tell the MPI library that you expect a particular kind of interconnect topology in your application, and then MPI can try to map your demanded topology to what is really available in the particular system. You can use complex data types if you want to. You can also create your own communicators or do subgroups in order to restrict your collective communication to a fewer set of nodes inside your overall application run. Error handling, profiling is supported, so there's a lot of stuff available. MPI is well documented and it's the de facto standard in supercomputing world. Meanwhile, it also has shown to be feasible in commercial environments, in industrial applications. It mainly depends on the question wherever you want to invest the time to write a so-called low-level message passing application that performs all the synchronization based on the given primitives. If you want to play around with MPI, there are open source implementations available free for download, for example, the MPitch library or the OpenMP library.